Today I'm going to talk to you about some of the new technologies that have become available for us to better formulate our animal feeds. I'm going to talk particularly about NIR technology, both hardware and software, and how we can use this to optimize our feed production. We all understand that there is a variation between different raw materials, and you can see here when we look at the phytate P content of these different plant-derived feedstuffs that the phytate P percentage content can vary between essentially 0 up to 2%. So there is a wide variation between raw materials, and we all understand that. What we tend to understand somewhat less is the variation within a raw material. So if we look at soybean meal here as an example, the average phytate P content is around 0.4%. However, it is not unusual to find soybean meals with a phytate P content as low as 0.3% and as high as 0.5%. So we have variation both within raw materials and between raw materials that we need to understand better. Recent advances in near-infrared technology will allow us to understand this variation both within and between feedstuffs better. There are today different types of equipment, for example laboratory equipment, that has advanced remarkably over the last 10 years that we can use in our feed mills. There are also, over the past 1 or 2 years, we have become available miniature equipment which have been built into some very, very robust handheld units. And again, these can be used not just in the feed mill, but can be taken out on the farm. And lastly, we have a progression from, for example, the pharmaceutical industry into the animal feed industry of inline equipment. So we have had a number of advances in the hardware side, but we've also had advances in the software side. And one of the major ones of these is the availability of online calibrations that we can use on our NIR equipment. And an example of this is the feed quality service provided by AB Vista. If you want to develop a calibration, it actually is quite costly and it is time consuming. I think the best way to do is to start with 100 samples of a particular raw material, in this case corn. You then run these 100 samples of corn through your NIR and you send them off to an accredited laboratory to get them analysed by accredited methods. When you have the 100 analyses from the laboratory and the 100 NIR spectra, providing you have wide variation within those samples, you can probably then build an appropriate NIR calibration. And you can use that calibration then to predict the composition of corn going forward. But as you go forward, because there are changes in cereal cultivars, there are changes in the way grains are grown, you will need every year to repeat this process, probably with up to 50 different samples every year. And this will go on as long as you wish to use that calibration. So to build a calibration is time consuming and it is costly. And remember, this is just one calibration. You need to repeat this for all your feeds and all the feedstuffs in which you have interest. However, you need to keep in mind that different NIR equipment have a different wavelengths. So if you look at the benchtop, they quite often cover wavelength the whole way through from visible light through to microwave. So from around 400 nanometers up to 2500. However, some of the other equipment, some of the other units cover a different wavelength. And therefore it is not possible to take a calibration developed for a full spectrum machine and put it onto a limited spectrum unit. So you need to develop different calibrations for different types of equipment. One of the comments I most frequently hear from people who have just started to use NIR is that the results they get from the NIR unit is different than those they normally get from the laboratory. There are a number of reasons for this, but the first one we need to examine is the error within sampling, the error within preparation, and the error within analysis. So if the same sample was not used or the preparation was different, then you will find a different result. And of course, you always get analytical error when you send samples off for analysis. So you need to understand better the error you can expect within your sample. The other thing you need to bear in mind is that if your calibration is built using one analytical method and the laboratory is using a different method, then you would expect the results from those two methods to differ. So for example, if you're measuring moisture and the NIR calibration is built using a conventional oven with overnight heating, and the wet chemistry laboratory is using a microwave for a few minutes, then the results will differ because the assay methods differ. You also must remember that the NIR calibrations are built off wet chemistry, and therefore the errors that you find in wet chemistry are built into those NIR calibrations. If you look, for example, at crude fibre, you can see that the uncertainty in the analysis of crude fibre for a sample with around 5% crude fibre is around 12% or 0.06. So again, there is a built-in variation both in wet chemistry and in the NIR that you have to understand and accept. So in fact, if you send a sample off for analysis in two different laboratories, whether by wet chemistry or by NIR, the chances are you will get slightly different results. But if those results fall within the uncertainty of the assay method, then those results are acceptable and you can use those results. So now that we've calibrated our NIR, we need to look how we can use this equipment to make decisions regarding our feed formulation. And I'm going to look at three different areas of economic importance. I'm going to look at phytate and then energy, and lastly we will look at amino acids. And if we look at the 120 pig feeds here, we can see that phytate P percentage varies from as low as 0.1% up to as high as 0.5%. If you have a phytase such as quantum blue that can release up to 80% of this phytate P, that means you're releasing somewhere around just under 0.1% up to around 0.4%, which is a big effect on the economy of producing feeds. We can help understand this variation a bit better if we split the feeds into species. So we see here in the piglet feeds, which generally have higher levels of animal protein, the phytate P content is lower. And if we look at sow gestation diets, which have higher levels of high fibre feedstuffs, we can see that the phytate P is much higher. However, the variation within each of these groupings is still more than double. So you need to understand what the phytate P content of your diet is before you make decisions on how much phytate you can add to this diet and what costs you can save. The second area I would like to look at is energy, and particularly energy of different cereals. And this is data from an experiment we were involved in where we fed almost 300 different cereals to different animal species, including broilers, layers, and growing pigs. And this is the growing pig data. And you can see quite clearly here a difference between the different feedstuffs, but you can also see a variation within different feedstuffs. So the variation between the feedstuff is around 1.5 megajoules, and the variation within each feedstuff is also around 1.5 megajoules. If you consider that a megajoule of energy is worth somewhere between 5 and 20 euros in a feed, and we produce more than 500 million tons of monogastric feed per year, then you can see that understanding the energy value of your feedstuff is of big economic importance. The last area I'd like to cover is amino acids, and particularly lysine. As you heat process lysine, it loses its usability for the animal, and what you need to look at then is reactive lysine, which is a measure of the lysine which is available for the animal to use once digested. Here we've analysed around 300 samples of soybean meal, and we find that in good quality soybean meals, the reactive lysine is normally around 90 to 95, even up to 99% of the total lysine. However, if you overprocess soybean meal, this reactive lysine percentage can drop considerably. This is the type of information you need to understand if you're going to make decisions about where to source your soybean meal. And these calibrations are available online through the AB Vista feed quality service. So there are a number of equipment options available to you. There is, for example, laboratory equipment, there is inline, and there is mobile or handheld equipment. There are also a number of calibration options you can look at, including to build your own calibration, and that is most common, for example, for proximate analysis. But you may want to go outside to get other more expensive analyses, such as the in vivo energy values or the reactive lysine. There are also other applications of NIR you can look at. For example, you can look at identification or traceability, and you can look at mixability of your diet. So to sum up, you need to understand the right type of equipment for you. It may be, for example, just a laboratory unit, or it may be a combination of laboratory, handheld, and inline units. Once you've made that decision, then you need to look at your calibrations, and the calibration needs to be suitable for your analyses as well as your equipment. The third thing you need to think about is what to do with the data. My recommendation is that you analyse a wide range of samples. You try to understand the variation within the samples and between samples from different sources. When you have that information, then you can start to make economic decisions that will help you maximise your profitability. Thank you.